So, welcome to Sundar's lecture, and this is lecture number 3 on basics of resistors, inductors, and capacitors. So, in the last class, we have seen inductors, right? We have taken an inductor and we have connected it with the voltage source, and we have seen that after applying this voltage source, what are all the currents flowing through the inductor? At 5 seconds, we have found 6 seconds, 7 and 8 seconds, we have found already, and we have concluded that the current in the inductor is increasing linearly with respect to time. That is what we have concluded. Then after 5 seconds, what we have done, we have short circuited the inductor and the voltage across inductor becomes 0. And if that becomes 0, and we have found an expression that there will not be any change in current. And so we have uh, found finally that this inductor will have 25 amperes of current forever. And with that, we have understood that this inductor is capable of storing energy, and how much of energy it is storing, that is what we are going to see in this lecture. So you see, so I will draw the diagram anyhow. So I will write down the topic first: energy stored in an inductor. Energy stored in an inductor, right? So if I want to draw the diagram, so it is very simple. This is voltage source and this is the inductor. Now I am just drawing the diagram. So this will be plus minus B, and this is nothing but I, and this is what is the, this is L. What is the voltage across this inductor? L into di by dt, right? So now if I want to find what is power, P of t will be equal to VL into I in inductor. I am just writing the power expression for the inductor. So this inductor will have power V into I, right? So here, what is VL? VL, which is nothing but L into di by dt into I. So this is the power expression. And if I want to find what is energy, energy will be equal to power into time, right? Power into time. For I'm assuming for small amount of time dt. So assume dt time, small time dt. So how I can write this? Energy can be, so that also dw, that is nothing but w is energy, and I am assuming it for the small time, so that I am just writing dw will be equal to p of t into dt, right? What is p of t we have found? What is p of t we have found? That is nothing but L into di by dt. So L into di by dt into dt. So this is dw. So this dt and this dt will be cancelled out, and if I want to integrate on both sides, this becomes dw, and this will be, sorry, here I have missed I here, I, because you see it is L di by dt into I is there, so I have missed I, so you put I here. So here it will be L is constant, so this is I into di, right? Now now you have to understand, so this becomes this dw becomes w now, because we have integrated it. So this is nothing but w, which is equal to L into integration of I into di. And what is the limit of this integration? And we have seen here, you see, we have seen here, inductor is storing current. Always it receives current from the voltage source. So now I, and also we have seen that if you short circuit the inductor at a particular time, the current will be stored in the inductor. right? So it is receiving current from the voltage source whenever it is connected to the voltage source. So I need to, if I want to find what is energy stored in the inductor, I need to know how much of current it is getting from the voltage source from the beginning. So what I have to write as a limit here, this is nothing but this is 0 to I. How much of energy that I need to integrate. So you try to understand. So if I integrate this, this becomes L into, so if you integrate I with respect to I, so you will get I square by 2. So I square by 2. So what is the limit of the integration? This is 0 to I. So if you substitute upper limit I is, instead of I you need to substitute I, and minus instead of I you need to substitute 0. So this will be L into, again I, instead of I am just substituting I by 2 minus 0 square by 2. So this becomes 0. So you will get what? I am just writing 1 by 2 Li square. So what is the final expression now? For energy stored in an inductor, that is nothing but half Li square. Half Li square. That's all. So this is the final expression for energy stored in an inductor, right? Now, I'm just going to substitute all these values for the previous problem. So whatever we have taken in the last problem, you see, inductor value is 1, and after 5 seconds, I'm just going to find after 5 seconds what is the energy stored in the inductor. Then that will be stored forever, and you need to understand, right? So you see, so after 5 seconds, what we have told you, what I have told you, so inductor value is 1 Henry, that is not going to change. And what is the current there? Current, which is nothing but it is 25 amperes, that is stored forever after short circuiting the inductor, right, at 5 seconds. So now if I want to find how much of energy it will be stored in the inductor, that is nothing but 1 by 2. This is 1 into 25 square. And what is 25 square? That is 625. 625 divided by 2, you will get 312.5. So you can write that energy stored, which is nothing but 312.5 joules, right? This much of energy will be stored in the inductor after 5 seconds, right? So what are all the points we can consolidate here? We can put a note here. Note, first point, inductors are memory elements. It stores memory elements because it stores energy, right? So it can store energy. So I am writing this is memory element. If you come to this point, to the previous lectures, there you see we have a expression for I. You see this I. If I want to find what is the I, that is present value of current in an inductor, you need to integrate V. Integrating V means you need to get all the values of V from minus infinity. That means past histories of V should be known to find the present value of current, right? That is why this inductor is a memory element. Since it is a memory element, whatever the voltage applied to this inductor should be known to find the present value of current. So I can write like this, right? I can write the second point, to find present I, past voltage or past voltages are required. Past voltages are required, right? So this is what inductor, the basics of inductors, right? We have seen the basics of inductors. This inductors can store energy, and if you want to find what is the present value of current, you need to know what is the past histories of voltages, right? So we will go to the so now we will see what is the capacitors now. So we will take capacitors. So capacitors, right? So for capacitor, I need to draw a diagram. Okay. So this is the current source and we are giving current here, and this is nothing but switch, and current will be I here, and this is capacitor, and voltage between this capacitor will be V, right? I am assuming it as V, right? So one thing I just want to tell you before going to explain what is capacitor. The only difference between capacitor and inductor is nothing but here, there we have seen current will be stored in the inductor, and here in capacitors voltage will be stored, and whatever the current expression we have seen there, that will be here, it will be as a voltage expressions. And if you want to find what is energy stored in the capacitor, you can see that we will derive it anyhow. There it is half Li square, here it will be half Cv square. Instead of current, we will have voltages here, right? Anyhow, so what is the current in the capacitor? How we can write that expression? I will be equal to C dV by dt. That we know already, right? This is expression number 1. And I need to find what is voltage here. So in inductor we would have found what is current, but in capacitor we need to find what is voltage, since capacitor will store and voltages. So if we want to find this one, so this dV by dt will be equal to this one 1 by C I, and you bring this dt to other side, bring this dt to other side, so you will get that dV will be equal to 1 by C I into dt, right? So if you integrate on both sides, this will be dV, this is equal to 1 by C integration of I into dt, right? So this becomes V will be equal to 1 by C integration of I into dt, right? So this is how you will get the expression. And now you see what is V here we have written. So V will be equal to 1 by C integration of I into dt, right? So now I am assuming that this capacitor is not has not carried any current before the starting of before start. This capacitor is not carrying any current. I am just assuming that. So what I can write now, so V will be equal to 1 by C integration of 0 to, I need to find some time, that is t, into I into dt. So this is how my expression will come. So again we will assume the values here. So let C is equal to 1 farad and current I is equal to 5 amperes, right? 5 amperes. So this current, which is nothing but it is 5 amperes, and this capacitor, which is nothing but it is 1 farad, right? Now you substitute and you find the value, right? 1 by 1 integration of 0 to t, and this current will be 5 into dt, right? Now I need to find what is the voltage at 5 seconds. So what is that? T is equal to 5 seconds. At 5 seconds, which means V of 5 will be equal to, this 1 by 1 will be 1, we don't need to write that. So this becomes 0 to 5, 5 into dt, right? What you will get? 5 constant integration you will get 5t, and what is the limit? 0 to 5, and what you will get? 5 into 5 minus, sorry, so 5 instead of t you have to substitute this, minus 5 into 0, and you will get what? 25 volt, and this is the V of 5. And if you find for t is equal to 6 seconds, and what you will get? You substitute in this expression, so you will get V of 6 will be equal to 1 by 1 you just leave, so 0 to 6 dt, right? Sorry, voltage will be 5, sorry, current will be 5 into dt, and if you find this, so you will get what? 5t, so you will get 0 to 6, and that is nothing but 5 into 6 minus 5 into 0, and you will get V of 6 will be equal to 30 volt. And if you find V of 7, that is nothing but 5 into 7, that is nothing but 35 volt. You just substitute, and V of 8 becomes 40 volt. 40 volt. So now you see, whenever I have applied a current to the capacitor, the voltage in the capacitor with respect to time, it is increasing linearly. That's all, right? So I will draw the graph. You see, this is x-axis, this is y-axis, right? So this is x-axis, this is y, this is x-axis, this is y-axis, and you see this is V and this is time. So what happens here? Your voltage is increasing linearly here, and up to what extent this voltage can increase? That is the, again, a $1,000,000 question. How much of voltage that this capacitor can possess? That is the first question. So again I will assume that this capacitor rated voltage is, just we assume that it is 25 volt, right? Again, so 25 volt. Then what I have to do? I have to cut down the current after 5 seconds. You see, after 5 seconds I get 25 volt. If I supply the current to the capacitor after 5 seconds, at 6 seconds it becomes 30 volt, at 7 seconds it becomes 35 volt, right? So this capacitor will be busted again. So for that, what I will do here, you see, I will write here, at 5 seconds I am just going to open this switch. I will open this switch. So open switch. So if I open this switch, what happens? This current becomes 0. Since current source is open circuited, then this current will be 0. So what happens there? I will be equal to 0, right? So now you take from 1, expression number 1, you see, from this expression. So what I have done? I have made current to 0. So C into dV by dt. So this C, if it comes to the left hand side, that also becomes 0. So what I will get finally, you see, dV by dt becomes 0, right? So if dV by dt becomes 0, then this expression tells us there is no change in voltage, no change in voltage. Then what happens? At 5 seconds, this capacitor is having 25 volt, and this 25 volt will be stored forever. That is what we have seen in inductor too. There we have seen that current stored forever, but here you can easily see that dV by dt becomes 0. So that 25 volt will be stored forever. Simple, very simple, right? That is what I have told you already. You can clearly understand that whatever the whatever the content we have seen in the inductor, instead of current you just replace it with voltage. That is nothing but it is capacitor. Okay, fine. Anyhow, so now we will see how much of energy that. So now we have concluded that some amount of here you see voltage has been stored in the capacitor, so that obviously some energy will be stored, and how much of energy will be stored in the capacitor, that we will see, that we will derive it again. So energy stored in capacitor, energy stored in capacitors, right? Energy stored in capacitors, and we know we can draw the diagram. This is I, and this capacitor will be connected like this, and what is the current in the capacitor? That is nothing but C dV by dt, and this is capacitor, and this is nothing but I, right? And what is the voltage? Voltage across this capacitor will be V, right? Right. Now, if I want to write what is the power expression, that is P of T will be equal to V into I, right? V into I. That is in the capacitor. So, V will be equal to what? That is nothing but it is V. What is I? That is nothing but C into dV by dt, right? So, this is the power expression. And if I want to write what is energy, energy expressions will be equal to P of T into T, right? And if I want to write it for a small time dt, so what I can write, instead of E I will write W, that's all, right? So dW will be equal to P of T into dt, and you see what is P of T? CV into dV dt, right? So this is nothing but CV into dV by dt into dt, and this dt will be cancelled out. This is dw, and if I integrate on both sides, so integrate, so dw will be equal to C is constant, V into dV, right? So this becomes W directly, and you see what is the limit I have to write here. Again, same thing. What is this capacitor is storing? The capacitor is storing voltage, and if I give current to this capacitor, the voltage is linearly increasing. That means this capacitor will store voltage. At last you see, if I open circuit this current, this capacitor have 25 volt forever. So I need to find what is the voltage from 0. If I want to find what is the energy source, so this becomes 0 to V, which is nothing but dV. So if I integrate, so C will be there. If I integrate with respect to same thing, that is nothing but it is V square by 2, and what is the limit? That is nothing but 0 to V, and this is now becomes C, that is common. V, instead of V I have to substitute V by 2, V square by 2, then this is 0 square by 2, and what I will get at last, so that is nothing but C V square divided by 2, right? So I can finally write what is W. W will be equal to 1 by 2 CV square. That's all. This is the final expression, right? So if I want to find what is the energy stored for the previous problem, and you see we have assumed that C is equal to 1 farad, and what is the voltage at 5 seconds? I need to find at 5 seconds, it is 25 volt. So at 5 seconds, at 5 seconds, I need to find what is the energy stored. So W is equal to 1 by 2. Capacitor we have assumed 1 farad, and voltage, that is nothing but 25 square. And what is this value? This is nothing but 625, and divided by 2, that is nothing but 312.5 joules. That's all, right? So this amount of energy would have stored in the capacitor. and we need to consolidate this, and we can write now note and capacitor C is C is memory element, right? C will be memory element, that we know since it is storing energy. And second point, to find present V, what that means voltage, we need past I, right? Past history of I, past history of I. You see this expression so that you can easily understand. And you see this expression, that is that you see, yes, this one. You see, V is equal to 1 by C integration of I, right? So if you want to find what is the present value of current, you need to know what is the previous histories of current values, right? So that is what we have written here. So this is the basics of resistors, inductors, and capacitors. We will conclude with this lecture, uh, and I want to tell you that I will continue to post videos related to circuit theory. So that is why I have started this lecture. So I need to explain you what is the basics of resistors, inductors, and capacitors, and then I want to continue to explain the basic electrical networks, how to solve the electrical networks by mesh current analysis method, nodal voltage analysis method, and several theorems. So I will post videos related to electrical networks, and at last, after completing all the lectures, I also going to solve the gate questions. So that is the ultimate aim of this lectures. Please watch my lectures, and if you have any doubts, please post in the comments, and I will reply for the comments. So please follow me, and we will see what is the resistors connected in parallel, expression for resistors connected in parallel and series, and we will try to solve the resistors, simplification of resistors, and Kirchhoff's voltage law, current law, all the basics we will see, and then we try to solve the electrical network by mesh current and nodal voltage analysis, and also we will go to theorems. Thank you.